Hi everyone, I'm Long, and thank you for your patience. I'm majoring in electrical engineering, and this is my partner Luke, majoring in computer engineering. We're here to present you the Hexagon project, part identification using a collaborative robot. The scope of this project is to create an automated inspection system. The system now consists of 3 separate components. As you can see in this picture here, on the left is a cabinet of multiple drawers that contain parts that need to be measured. And in between the cabinet and the coordinate measuring machine on the right of the picture is our robot. The role of the robot in this system is to transfer the parts from the cabinet to the coordinate measuring machine for it to measure the precise coordinates of the part. This method, before the robot can perform its routine, the parts need to be manually loaded into the drawers, and the data about these parts need to be manually entered into the system as well. This method not only creates additional costs for the company, but also is prone to human error. With that being said, that motivates our project to focus on these 3 objectives. There are no human intervention, no single object data entry, and no human error. The best anticipated outcome for our project is to create a reliable, robust, and user-friendly object recognition system that combines our hardware design and software system to eliminate human error and improve the inspection system as overall. The implementation of our design will not only reduce the labor costs for the company, but also optimize the inspection process and ultimately improve the efficiency and traceability of the system. On the hardware end, we're going to use multiple Raspberry Pi cameras, and we're going to mount each camera above each drawer for it to capture a real-time image data, which will then feed into our software system for it to train our neural network model. So one of the goals we're trying to accomplish with our hardware design is to detect the condition of a drawer. We're going to use multiple ultrasonic sensors, where we're going to install each sensor on above the drawer. So the sensor can measure the range in between the closest drawer to the sensor. We will use this value as our threshold for each drawer. So if the received value by the sensor is exceeding this threshold, we can state that the drawer is being opened. With this information, we can determine which drawer is being opened and effectively locate the drawer that contains misoriented part.
This block diagram visualizes the software aspect of the project that we're going through. It consists of 4 main scripts to perform the tasks that we need for object detection. To start off with, after we detect which drawer is open, we want to be able to determine to take a picture of the drawer at that time and determine whether there are parts loaded into the drawer and where those parts are located within the drawer. This takes part in the background segmentation script, which is segmenting the objects from the background and determining where they are located in the image taken real time. In addition, we have 2 neural networks, which were explained by Team Acumetrics. Ours, however, would be taking image data as opposed to inputs for power analysis. And that image data will be used to both classify the parts, determine which part it is, as well as to detect the orientation of the parts to notify if the part is loaded incorrectly or if it's loaded such that the coordinate measuring machine is able to pick it up properly. Finally, we have an output formatting script. This would be able to, if the part is loaded incorrectly or if a part cannot be identified, it would output an error as specified by Hexagon. And then, on the other hand, if it is loaded correctly, it would format into the appropriate JSON format that the Cobot expects in order to allow it to be loaded into the coordinate measure machine for processing. So our first key accomplishment, or one of our key accomplishments, has to do with the background segmentation script, as I described previously. Now, this script consists of two main methods that we used after doing research on different methods of background segmentation. The first method uses a background mask, or in this case, an empty image with no parts present that was taken previously, as well as a live image that was just taken and is ready to be processed. These images are compared by using a threshold and calculating the Euclidean distance between pixels in the image to determine if the pixel is different enough that it comprises the foreground of the image or a different object having been loaded from what the background would be. This can be seen in the top three images, where the first image is the live image of just a single part. The second image is the background image, so this is an empty scene with no objects present. And then the difference between those consists of the general location of the part that is to be loaded. The second method is a single image calculation where there is no background mask, so we need to determine where the parts are located in some other method. The method that we have selected after testing different background segmentation options or edge detectors is a phase congruence threshold. Then this can be seen in the two images below, where it is only a single image input, and then this is the return background mask, where it detects the object in the scene. Now, it is important for this script that it needs to return the number of objects present, the bit mask of the general object, and it also needs to return the object locations, as well as we would like to slice single object images so that these can be appropriately passed into the neural networks for processing. For more information on the phase congruence thresholding, essentially what it does is it performs a two-dimensional fast Fourier transform, and then it performs calculations on these in order to detect edges regardless of orientation. And these creates multiple orientation images, which we then combine and perform calculations on to detect objects present in the image. And then this is run on this object in multiple orientations. It's approximately 50 images and running through the script. For remaining challenges, we now need to focus on working on the detection aspect of the models. So we need to work on the object classification and orientation detection so that we can detect what parts are loaded and whether they're loaded correctly. And after that, we need to move on to transferring the output to the coordinate measuring machine in Cobot so that after they've been detected, we can produce the output that the Cobot expects so that it can load the part. And then finally, we need to perform further testing of our background segmentation scripts as well as our models to ensure that they behave properly in different lighting conditions or different backgrounds so that they're as robust as possible. I'd like to thank everyone that's helped us with this project.